Today we're going to talk about 3 empirical papers on tax incidence. But before I get to each of them, I want to give you kind of a high-level overview of the types of approaches that these papers and all the other papers we're going to talk about in this class take. And so all of the empirical studies we're going to consider here in this course start by formulating clear research designs. And I want to be very clear about why that is crucial in these studies and should be a centerpiece of your own work before we get into the details. So why do you want to develop what we're going to call an explicit research design rather than simply using all the available variation in tax rates? So one way you might think about approaching any of these problems is you get some big data set. There's outcome variables of interest. There are tax rates. And so then traditionally, like in the 70s and 80s, when people were starting to do this type of empirical work, you would just run a regression of whatever your outcome was on tax rates and then interpret that coefficient and not really worry about why tax rates were varying across people or why different people were being treated differently. So I think that paradigm has totally shifted, and I want to be clear about why that is. So let's consider estimating the effect of a treatment, for example, a tax T on an outcome Y. And let's posit that the true model is some linear specification where yi, the outcome for individual I, there's an intercept alpha, and then there's a treatment effect beta, where if I give you this treatment ti, it has an impact beta on the outcome, and then there's some error term. So now treatment in general is going to be assigned based on some model. I'm going to call it a selection model, where the treatment is a function of some set of covariates. For instance, maybe demographic characteristics, maybe people with kids face higher or lower tax rates, et cetera. So there's some vector x and some set of coefficients on that beta t which determine whether you get treatment or not. And then there's some unobserved noise that determines whether you get the treatment or not. Now, the key problem in applied econometrics is that treatment may be non-random, right? So that there's a covariance between x and epsilon I in the first equation, or there's a covariance between eta, the unobserved heterogeneity term in the selection equation, and epsilon I in the treatment equation. Now, what's the traditional approach to dealing with that problem? It's to account for the confounding factors, essentially a selection problem, by controlling for observables, right? So I include this vector xi in the regression that when I regress y on taxes t, the traditional response would be, sure, tax rates might vary across people in a way that's correlated with other factors, but I'm going to control for those factors directly in the when I estimate the treatment effect, right? And so then I get this coefficient gamma on that control vector, and supposedly the hope is that I get a consistent estimate of beta. Now, you can think about various techniques that you use to do that control. So many students will come and ask, well, maybe I shouldn't do an OLS regression, but what if I use a more sophisticated method of controlling for observables like matching? So matching is I find 2 people who have identical x's, right? Like in a big data set, I'm going to be able to find 2 people who have identical observable characteristics but face different treatments. Or I can do propensity score reweighting, where in a probabilistic sense, I match people up on characteristics, essentially, right? So these are all various methods of controlling for observable characteristics. But what I want to emphasize is that regardless of how you're doing this controlling, even if you do it perfectly, the problem with those approaches is that you do not know the source of the variation in the treatment TI, or the source of the variation in the tax rate in the examples we're going to be talking about. So to see what that problem is more clearly, notice that there has to be some reason that one person got treated and another did not, even if they're perfectly matched on observables. So to take an extreme example, which is often used in the literature in labor economics, think about studies of twins, where the idea of the twins research design is you've got 2 people who are essentially identical, and then one, for some reason, got more years of schooling than the other, and I'm going to use this to estimate the impact of years of schooling on, say, earnings or something like that. Now, while you can understand why people found that design appealing, I don't think a twins research design is actually very compelling, because we need to understand why one twin chose to get more education than the other, right? There's some unobserved reason that one twin got more education than the other. And so to put it formally in our notation here, eta I has to be correlated with ti in order to have variation in ti given xi, right? So the idea of the twins is I'm taking two guys who have exactly the same x, right? But one got the treatment, the other didn't. So obviously their eta i's were different. Now the problem is there's some unobserved reason. You don't know what that reason is. And so it could well be that the covariance of eta I with epsilon I in the treatment effect equation is non-zero. So in other words, that same unobserved factor, which made one twin get more education than the other, he was more motivated or whatever, got exposed to a different teacher, that factor could end up having a direct effect on earnings. And there's no possible way you could know whether that covariance is equal to 0 or not. So this is why I think the approach of saying I'm going to control for a bunch of factors very well is never going to be totally convincing, because you need to know what the source of variation that's driving your treatment effect actually is, right? Okay, and so then that's where a research design comes in. One way to think about what does it mean, like you often hear in the labor PF lunch, what is your research design, or be clear about your research design. Technically, what does that mean? It is in this context, what is the source of variation in eta I that's driving your identification? Where is that variation in eta I coming from? And in particular, do I think that source of variation is credibly unrelated to epsilon I, the error term in the treatment effect equation, right? So to take one example, suppose I have a reform that affects people above age 65 but not below. So this is a common design that's used like to study Medicare, the impacts of Medicare. So what's the idea here? People at age 64 and 65 are likely to have similar outcomes. We don't think that, say, health outcomes are going to vary very sharply with age, okay? And so we can compare just people just below and above this cutoff, and we think it's pretty credible to assume that the covariance of eta I and epsilon I is 0 because you have specified where the variation in the treatment is coming from. Okay, so that's the research design-based approach, which is very different, I think, from the more structural approach where you're guided by a particular model on what these covariances look like. Here it's more like, I've got a pretty strong argument for why I think this covariance is 0, and so I know exactly where my variation is coming from. And at least, I would say in applied micro, that's the bar you have to meet in empirical work today. Now, in other fields of economics, like in macro, you're still fine even if that is not true, but that's a separate problem. So what I want to point out generally is the idea of controlling for confounding factors using regression or reweighting, whatever technique you use, is really going to give you convincing estimates. Now, one caveat to this point is that reweighting can be a useful technique to obtain better control groups when you're pairing it with a quasi-experimental research design. And we'll talk about examples of this later on in this lecture and later on in the course. In particular, using this technique in this paper by DiNardo, Fortin, and Lemieux in Econometrica in 1996, which we'll come back to later. So any questions just about that basic logic? Okay, so let's start with the first paper on cigarette taxation. So the question in this paper is very simple. How does cigarette tax increases affect prices? Why do we care about that? We want to know whether when we impose these big cigarette taxes, are we taking money away from the big tobacco companies? Are we reducing their profits? Or are we taking money away from typically the relatively low-income consumers who are smoking cigarettes? Now, one reason to start with this application is that the partial equilibrium framework, which is kind of guiding the way we think about incidence, is a plausible approximation for cigarettes, right? We don't think taxes on cigarettes are going to have big income effects. And at least a first order, you might not worry about complementarities or substitutability in the utility function. So we're going to use that framework here. So just a bit of institutional background. Cigarettes are taxed at both the federal and state levels in the US. Generates total revenue, state plus federal, of about $35 billion a year. So that's relatively big. It's on the order of estate taxation, which people care a lot about, right? The federal tax remained relatively constant for a while, but then recently in 2009 increased substantially from 39 cents a pack to over $1 a pack. And then there's tremendous variation across states. So 30 cents per pack today in Virginia versus $4.35 in New York. Okay, so that type of variation, A, is interesting from a policy point of view, which of these is sort of the right tax rate, and B, from an econometric point of view, gives you a lot of variation to estimate the treatment effect of interest. Now, people are also interested in cigarettes, aside from the pure incidence question, because of health and paternalism concerns, right? So even, as we'll talk about a little bit later, you might think that even if the incidence of the tax falls on the consumer, so they pay higher prices, that might actually be a good thing because we want to deter people from consuming cigarettes, possibly. Okay, so what these authors do is exploit the fact that since 1975, there have been more than 200 state-level tax changes in cigarettes, and so that gives you lots of natural experiments to investigate tax incidence. And they're going to exploit those state-level changes using simple diff and diff research design. So this paper turns out to be a good way to introduce and think about more rigorously what the assumptions and pitfalls of diff and diff research designs are. So what's the most basic idea? Let's think about the federal tax change. Suppose the federal government implements a tax change, like it did in 2009. What's the simplest possible estimator with that research design? Let's compare prices before and after the change, right? Okay, PA1 minus PA0 in this notation. The identification assumption here is that absent the tax change, there would have been no change in cigarette prices before versus after 2009. Now, naturally, that's a very strong identification assumption, and we don't think it's typically plausible because there are various reasons that cigarette prices might fluctuate in the time series. So this is more generally, I think, the problem with a pure time series analysis. You have no counterfactual except prior periods, and we don't think that things are necessarily stable in time series. And so if prices are fluctuating for whatever reason, the first difference or time series estimate is going to be biased. And so then that naturally leads you to a difference in difference estimator where, say, we have two states, A, that experienced a tax change, B, that does not experience any tax change. And quite intuitively, you look at the change in prices in A after minus before versus the change in prices in B to remove any trends. Okay? What's the identifying assumption there? We already talked about this in the previous lecture. It's the standard parallel trends or common trends assumption, which is that absent the policy change, the price change P1 minus P0 would have been the same in states A and B. So you would have gotten a DD estimate of 0. We're going to make this parallel trends assumption. So now let me show you two examples, graphs taken from their paper, one that I think is convincing and one that's not that convincing. And this actually relates to a question that Vijay, you had raised in the previous lecture about how do you do placebo tests in the diff and diff setting, more generally. So, okay, so take these two examples where they're comparing in the upper panel here. Y-axis is log per capita consumption of cigarettes, okay? And then this is where there was a tax reform in each of these states, in Michigan and Arizona, where they raised taxes on cigarettes significantly, okay? Shown by the vertical line here. Now, the upper panel compares Arizona to the US as a whole. The rest of the US is being used as a counterfactual. And then the lower panel is comparing Michigan to the rest of the US, all right? So you can see right away that the Arizona one is not really very convincing, right? The problem is that there are clearly differential trends well before the policy change actually occurs. And so I don't have that much confidence that this dip that occurs after the tax change relative to the flat line there is purely due to the tax reform, because the same thing happened here as well, right? And in other places. So a couple of things to notice from these graphs, the reason why it's useful to plot this. First of all, you can kind of assess the identification assumption. So coming back to your question, sure, policy changes might be endogenous, but look at the case of Michigan right here. That really sharp treatment effect after the trends were really parallel makes you think that that's probably the causal effect of the policy and not endogenous policy change. Because think about how the endogenous policy change would have had to occur. Like something changes in Michigan where you're anticipating that demand is going to fall a lot, and then you end up changing taxes, which seems kind of weird. Whereas here, it seems plausible that the policy change might have been endogenous to whatever differential stuff was going on in Arizona relative to the rest of the US, right? So the point that I'm trying to make here, and it ties back to the other question about placebo tests, is by looking at a long time series of changes, of relative changes prior to your actual reform of interest, you're effectively, with your eye, doing a permutation test, right? You're effectively saying, suppose the reform had occurred here, 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 and all these other places, I would not have found a significant DD estimate, but I am seeing a really significant differential trend right at this point, so I'm convinced that there's a treatment effect here. Whereas with this one, it doesn't really pass the permutation test. Now notice, in contrast, that if I had just shown you a table with pre and post values for Arizona and the rest of the US, and done the same thing for Michigan, the two tables would have basically looked equally good. You would have seen a pretty big average drop in Arizona relative to the rest of the US, relative to pooling the whole pre-period. And so by just showing the regression output or just showing the table with 4 means, you are seriously masking the amount of information you communicate from the data, because it's just, you're putting a lot more parametric structure on the problem than if you actually plot the 2 series. Okay, so this non-parametric approach, because you're seeing so many contrasts visually, you can figure out whether the design actually looks credible. Right? Any other questions about this? Okay, so that's the basic idea. We use the placebo DD to test the parallel trends assumption. It's analogous to the permutation test that we described in the last lecture, as I was just saying. You're essentially pretending that the reform occurred at other points and replicating the estimate visually, if not numerically. Now, and this just reviews what I was just saying. If the DD in the other periods is not 0, then the DD at the time you're looking at, t equals 1, the treatment is likely to be biased. And so it's useful to plot the long time series, et cetera. Okay, so now some studies use a triple difference to try to account for the fact that there are differential trends. So let me come back to this here. I see in Arizona versus the rest of the US that there are differential trends even before. And as we talked about in the previous lecture, I can then account for the fact that there are these differential trends and try to further difference out those differential trends, forming the triple difference estimate. So let's talk about whether that actually is convincing. So we talked about an example with the grocery stores where we did that, the difference in the treatment stores and then the difference in the control stores, and then formed the triple difference. And as I pointed out there, I see the DDD as mainly being useful as a robustness check. So in the grocery store case, we were reassured to see that this difference and difference was 0. But if it was not 0, I don't think you can really make a convincing argument that the triple difference is removing all the bias. Because, come back to this example here. So you're going to, say that I see Arizona diverging from the US at some rate in the pre-period. And then I'm going to assume that that rate stays constant in the post-period. But really, that's not that convincing, right? I mean, those trends, they look there's a relative slope at this point, but the relative slope looks different in earlier years. You're getting into too much of a, you end up making basically too many assumptions to get your final estimate, and I think you're never going to find that it's convincing to people. So anytime you have to do 7 different things in order to get your final treatment effect, I think people are often skeptical, and rightly so, of whether you've actually identified a causal effect. So I think these types of triple differences are basically useful as a specification check, but I would not see that as the primary thing that you're going to do. Okay, so let's now generalize this. So remember that what they have in this study is not just Michigan versus the US or Arizona versus the US, but many such changes over many years. So how do you generalize the diff and diff analysis to having many treatments? Okay, so that's essentially what a fixed effects regression is. So they have data for 50 states, 30 years, many tax changes. You want to pool all that data to obtain a single incidence estimate rather than drawing a separate graph for each of the 200 experiments. So what we do is a fixed effects estimator, which generalizes DD with S greater than 2 periods and J greater than 2 groups. So suppose that group J in year T experiences a policy T, like a tax, of intensity T sub JT. So you can think of that as the tax rate, okay? So we want to identify the effect of T on the price P, right? That's the incidence question. So we think about running an OLS regression of prices on taxes to estimate the incidence parameter beta. Now, with no fixed effects, that estimate of beta is going to be biased if the treatment is correlated with the error term. So that's exactly the problem we were talking about at the beginning, where if you have no research design, you don't know what's driving that variation in tax rates. It could be correlated with all kinds of things. So for instance, if you're just comparing in the cross-section states with high cigarette tax rates versus states with low cigarette tax rates, you worry that the states with high cigarette tax rates, there's more anti-tobacco sentiment in general. And so, maybe they have more ads telling you about the problems with smoking, et cetera. And so then all of that's going to get loaded into this beta term, possibly, depending upon how all that stuff affects prices. And it's going to bias your estimate of the impact of the tax, right? Okay, so what's the solution to that? If your research design is to exploit these differential changes, the critical assumption being that there are parallel trends absent those changes, which requires, for instance, that the policy changes are not endogenous at high frequency, then the way you would do that is to include state and time dummies to get rid of the variation that's coming cross-sectionally across states or coming from the pure time series, right? So we include the gamma t dummies, the year fixed effects, and the delta j dummies, the state fixed effects. And one useful way to think about what a fixed effects regression is doing then is to think about a partial regression. So often when you're including these covariates, the way I like to think about it is whether it's fixed effects or some other vector of covariates that you're conditioning on for your research design, think about a partial regression or a residual regression where I first regress the price on the dummies, okay, on the year and state dummies, and then I compute the residuals. Okay, so another way to think about that is define p hat jt as pjt minus pj, which is the mean price in state j, minus pt, which is the mean price in year t. So those are going to be the estimated state and year fixed effects, right? All the fixed effects are the average values. And so then this is like saying, what is the deviation in the state from the state mean and the year mean? So what's the residual in that state? And then what you can establish from basic econometrics is that the coefficient beta that you get from this regression is the exact same coefficient you'll get if you regress p hat on t hat, where t hat are the residual tax rates defined in the same way. Okay, so one way to think about it then is that identification of the treatment effect beta in the fixed effects model is being obtained purely from residual variation within states over time after you've taken out these state and year fixed effects, right? And so then the identification assumption is that t hat has to be orthogonal to epsilon. So these residual differential changes across states can't be correlated with unobserved determinants of price, all right? Now, one thing you'll note comes back to the earlier question of are we using the federal tax change? So here it's clear that we are not using the federal tax change, right? So the fact that tax rates went up in 2009 at the federal level is not providing us with any identification because that's completely getting absorbed in the gamma t term. So it's totally irrelevant that there was a federal tax change. It's being dummied out, yeah. But notice, like coming back to the functional form thing, one thing I'll point out is another way you might do this is rather than putting in dummies for each year, you put in something like a quadratic to take out quadratic time trends or some polynomial. That would be a parametric version of this estimator, right? I'm not allowing non-parametrically each year to have a different effect. I'm allowing for smooth trends. That involves different assumptions. In general, I think it would be less preferable than this non-parametric estimator if you have the data to do it. Okay. Now, what's the advantage of the fixed effects estimate? It's more precise because you're pooling several changes, right? I'm using 200 experiments instead of one experiment, so that's clear. The disadvantage, I think, is the fixed effects is a bit of a black box regression. Like if you just showed me a regression table with a bunch of estimates of beta from this fixed effects regression, I'm not sure I would be totally convinced that you've actually identified the causal impact of these tax changes. I would like to see the graphical non-parametric evidence like they show for Arizona and Michigan so that we understand more clearly we can do those permutation tests by eye, sort of what I was describing, right? Another useful kind of visual check, when you think about it from this partial regression point of view, is to scatter the residuals p hat versus t hat. So often people will say, you talk about using graphical methods like these scatter plots or time series, et cetera. How do I do that if I have controls? Well, just because you have controls doesn't mean you immediately have to do a regression. What you want to do is take out the effect of your controls, so residualize both the left-hand side and the right-hand side variables, and then plot those residuals. And remember in the first lecture I was showing those graphs of how you can get very different patterns that give you exactly the same regression coefficient? You can do exactly that type of visual assessment with these residuals, right? Even taking out, even though you only want to exploit the within state over time variation. And it's important to keep in mind, fixed effects has the same parallel trends assumption as difference in difference. As we just talked about, a potential violation is if policy reforms respond to trends and outcomes. So for instance, if tobacco prices falling makes it easier for states to raise tax rates, then you can get violations of this assumption. So usually the diff and diff stuff works well when you're looking at very high frequency changes. So I think endogeneity concerns like this become problematic when you're trying to detect like long shifts in the time series. But if it's a sudden break from 2008 to 2009, it's hard to imagine if you see a sudden jump in prices or quantities that somehow endogenously drove the tax change, because we think that policy is going to be endogenous over a long set of lags of what's going on. Okay, so what do Evans, Ringgold, and Steck actually do, and what do they find? So they implement first a fixed effects model for prices. They regress price on state and year fixed effects, covariates, and tax rate measured in cents. Okay, this is a specific tax. Then they also estimate demand elasticities using a fixed effects estimator, regressing log quantity on the same things. Okay, so they're doing an analysis of both prices and quantities. Okay, so here are the price regressions. So let's just focus on the first column. Left-hand side variable is state level price, right-hand side variable is the tax, all right? And you see the coefficient is 1. So what does that mean? When I raise the tax by $1, prices go up by $1. So the incidence of the tax is falling completely on the consumer, 1 for 1. What does that imply about the price elasticity of supply? What has to be true for the tax to be fully passed through? Thinking back to the...
Fully elastic.
Yeah, it's perfectly elastic. And does that make sense in the context of cigarettes, do you think? So why are we seeing that it looks like we're in a perfectly elastic environment? But think about the source of the variation.
Is there some monopoly power within the industry?
So no, I don't think it's about the structure of the production of cigarettes necessarily, or the structure of the market. Think about the level of the variation that we're exploiting.
Each state is a relatively small component.
Yeah, exactly. So we're basically talking about variation where one state raises taxes and other states don't. And now think about my supply decision that I can send more cigarettes to Delaware versus some other state. I'm basically going to be infinitely elastic in that supply decision at the state level. So this comes back to the point that when you estimate a treatment effect like this, it's very important to think about how that relates to the parameter you're trying to estimate. You can't infer from this that a federal tax change, which is arguably what you care about at the end of the day, is going to have 100% pass through to consumers. In fact, you would think the pass through might be significantly smaller, right? But this is what you're able to estimate with the state level variation. And it's useful, let's say, for a state policymaker's perspective, what are my citizens going to pay if I raise taxes? This is the answer to that question, okay? So, this is exactly, this slide is making that point. Okay, let's now turn to quantities. So now we're putting on the left-hand side log per capita consumption. And the way to interpret this is that $1 increase in the price reduces consumption by 25%. Okay, so delta Q over Q, or delta log Q, is 0.25, all right? So then from that, we can compute a price elasticity, and let's talk about how we do that. This is a price elasticity of demand. Why is it a price elasticity of demand? This is an important point, actually. So I'm regressing quantity on tax, right? How do I know that I'm estimating the price elasticity of demand in this case? And now remember that quantity is determined by the intersection of supply and demand, right? So how do I know that I'm estimating the slope of the demand curve? It relates to what we just talked about previously. Yeah, which is that supply is perfectly elastic. So in other words, we know that, let's see if I can get this to work. We know that the supply curve looks like this. So supply curve is going like this when I raise the tax by $1, right? And so what I'm estimating then when I see delta Q is purely the slope of the demand curve, right? And so that's why you can interpret these as demand elasticities, because of the incidence point. So, okay, so how do we get the price elasticity of demand? So what they're finding is that the elasticity of demand is minus 0.42. That is a 10% increase in the price, induces a 4.2% reduction in the consumption of cigarettes. How do we compute the price elasticity of demand when using variation from tax changes? Okay, so in this case, it's very simple because we have exactly this situation here where delta P equals delta T. So I have the $1 increase in the tax, and I know that that's exactly the increase in the price that the consumer faces. And so it's trivial to estimate the elasticity. I know what delta Q over Q is from my regression. And so what is that coefficient beta here? It's delta Q over Q. That's the percentage variable on the left-hand side, the log, divided by delta T, right? So you're saying per dollar of change in the tax, by how many percent is cigarette consumption changing? And then because I know that delta T equals delta P, I can simply replace delta T by delta P because it's a one-for-one thing. And I know that the elasticity then is defined like this. Normally, the elasticity would be P over Q times delta Q over delta P, right? But delta P equals delta T. And so it follows then immediately that the elasticity is just beta hat over P, where we usually take the price. We evaluate the elasticity at the mean price and the mean quantity in the data, and then I can get this number of 0.42. Okay, so very straightforward when you have the 100% pass-through. But in practice, you typically don't have 100% pass-through. So that is taxes and prices do not move together one-to-one. And so what do you do in that case? What you do is you instrument for prices using taxes. And so this leads to a technique that's very commonly used in public finance, which is using taxes as instruments for the prices of interest. So let's think about some examples here in the context of cigarettes, of course, but also in the context of labor supply. Labor supply is a function of your wage rate. So usually what we do is we instrument for your wage rate with the tax that you pay, because that's creating variation in wages where we understand where it's coming from, and that gives us the arguably credible research design. Or we think about the effect of capital taxes. What do investment decisions depend on? They depend upon interest rates. So we instrument for net of tax interest rates with tax rates, right? So you're going to see this technique again and again. So how does this work? It's a standard two-stage least squares application, but let's just review here. So the first stage, we're allowing for these state and time fixed effects again. The first stage is regressing prices on taxes, okay? So that's just this coefficient here. This is the incidence coefficient, right? It's how does a $1 increase in the tax affect the price? Okay, so that gives me beta in the first stage. Now the second stage, the way I want to think about this is I have an instrument for price. So now I have, let's say I generate fitted values off of the first stage, which I'm going to call P hat, right? Predicted values. So I put that here on the right-hand side, and I look at how quantity relates to predicted prices, okay? And so that gives me the second stage coefficient lambda, which is the elasticity of interest. How does a change in price affect quantity? Now, that lambda, I can't literally run the regression in this way because I'm going to get the standard errors wrong because I've just plugged in p hat and not accounted for the fact that there's estimation error in the p hat. And so that's what a two-stage least squares estimator does. It gets, you'd get exactly the same coefficient lambda if you did it manually like this, but you'd get the standard error being too low. So when you do IV reg in Stata, for example, it's giving you the right standard error, accounting for the imprecision in the estimate of the p-hat. Now, one thing that I think is useful to keep in mind when you're looking at these IV estimates is that really what matters and what you should be looking at directly is the reduced form coefficient. So what is the reduced form in this context? It's the relationship between quantity demanded and the tax rate directly. Okay, so that really is your source of variation here. It's the tax rate, and the types of graphs I'd want to see are how are tax rates affecting your outcome of interest, affecting the quantity demanded, the amount people are saving, the amount people are working. All two-stage least squares is doing is rescaling that coefficient to a unit that we are able to interpret. All right, so two-stage least squares mathematically is the ratio of the reduced form coefficient here, mu, to the first stage coefficient beta. So you can show this mathematically. And so lambda hat, the second stage coefficient, is just mu hat divided by beta hat. So let's think about the intuition for that. I raise taxes by $1. Suppose the incidence is only 50%, so prices only go up by 50 cents. So suppose I see that you buy 2 units less of the good when I raise taxes by $1. But I've only raised price by 50 cents, so what that means is you're going to buy 4 units less of the good when I raise the price by $1, right? So I just need to inflate the coefficient by 1 over 0.5, right? And that's exactly what two-stage least squares is doing. All two-stage least squares does is rescales coefficients from the reduced form to get them in the units that you're interested in at the end of the day. So what the point here is that what really matters is the reduced form effect. And then you rescale that using a two-stage least squares estimator, which is what they do, to get the elasticity true. Okay, so, but this is the general technique to estimate demand elasticities. Any questions about how this works? Okay, so one thing to note in Evans, Ringgold, and Stretch, which is also illustrative of DD estimators more generally, is that they capture the impact of a policy change before and after, just the year before and after the change in policy, okay? So what they're essentially doing, if you look at those initial graphs, they're saying right after the reform relative to right before the reform, how do prices and quantity change? Fixed effects also basically captures short-term responses. That's because we're modeling behavior as a function of the current tax, right, in the fixed effects model. So when we look at these models, we're putting in only the contemporaneous tax rate. We're not putting in the tax rate in the previous period or the period before that and so forth. Now, you might think, especially in the context of cigarettes, that it's quite intuitive that there'd be lagged adjustment. That is, you know, some people quit and then some more people quit, or some people don't start, and you gradually see a response. So here, the basic fixed effects estimator is going to be biased. And one solution then would be to include lags of the tax rates. But that really is not a great solution, because then you start to get into the endogenous policy problem and the common trend, potential violations of the common trends assumption. Now you're really asking for much more stability in the trends across these treatment and control groups over many periods, and not just sharply in that one period where you have the treatment. And so this highlights, I think, this fundamental trade-off in applied public finance, where often in the theory, we're interested in the long-term impacts of policies, but in empirical work, we're typically only able to estimate the short-run impacts very credibly. And so we face this tension between trying to, again, estimate the parameter we're actually interested in and doing something credibly from a statistical point of view.
What do you think about using something like, say, synthetic matching?
Yeah. So synthetic matching, so, okay, yeah, let me talk about that here. Let's come back to this graph. Yeah, okay. So here, Michigan and the US look like pretty good matches for each other, right? So what is synthetic matching? The idea is there are a bunch of, so there are 49 other states. Rather than just taking an average of all of them, let's find a set of states that actually look more like Arizona. And so, for example, they might be geographically nearby, or another way we might do it more directly is match on prior trends. So find a set of states. So this is like the type of work that Alberto Abadi does. Find a set of states that when you take a weighted average of those states, demand looks like it's trending very similarly in the pre-years. Okay, so then by construction, you're going to have two lines that move together very well there. And that's what I meant where reweighting can be useful or controlling can be useful in conjunction with a quasi-experiment. So here you have this sharp change in Arizona. You might be able to construct a good counterfactual by reweighting or by synthetic matching to tell you what would have happened in Arizona absent the tax change, and then you have, again, a credible design. Now, one note of caution there is that sometimes what people do, which I think is not appropriate, is match using the entire pre-period all the way up to the policy reform. And then obviously, by construction, you're going to get this graph where it matches perfectly, and then it'll diverge. So that's like not convincing at all, right? Because you designed the graph to look like that. So what you want to do is match, like let's say up to 1985 or something, and then show that even after you stopped actually constraining the two to look similar, they continue to trend together, and then they break apart. But that absolutely can be a useful technique, and we'll talk more about it in other applications. Okay, so the last thing that they do in this paper is they look at distributional incidence. Okay, so far we've been talking about incidence on cigarette companies versus consumers. But let's now break the consumers up into separate groups using individual data to see who smokes by education group and income level, and here's the key graph in that context. So here they're plotting by age rates of smoking, and then more importantly, by income quartile, okay, at each age. And you can see that at lower incomes, smoking rates are higher, and they are substantially higher. So what you end up finding as a direct consequence of that is the tax is regressive on an absolute level. So normally when we say a tax is regressive, what we mean is as a percentage, higher income guys are paying less than lower income guys. But here actually in absolute amounts, the lower income guys are paying more cigarette taxes than higher income guys. And so the bottom line of this study is that when you levy taxes on cigarette companies, at least at the state level, basically what you're doing is taking money away from low income people with no impact on the companies, okay? Which may not be, depending upon your welfare perspective, what you wanted to do. No, that's right. And so you make a good point. Usually when we think about incidence, we think about impact on prices and not impact on quantities. And let me explain why that is. So the price impact is a first order impact. So like if you write down the profit function, when I change the price or when I change the tax, mathematically, what I mean by the impact is first order is that the loss in profits when I change prices is proportional to P. But the quantity impact is going to be second order. It's like a triangle rather than a rectangle, because I'm only losing profits on these marginal products where the marginal cost was very close to the value at which I'm selling it. And so there's a second order loss, proportional to P squared profit loss. And so that's why from the perspective of thinking about direct impacts on distributional incidence, you're right that quantities should matter, but they have a second order impact. And so we usually ignore them. But for efficiency, the quantity is going to be the central thing, which we'll come to later. Okay, so let's talk about a few other considerations in the context of cigarette taxes before moving on to the next paper. So one thing that people have shown is that in the context of these excise taxes like cigarettes, gasoline, alcohol taxes, and so forth, they are much less regressive from a lifetime perspective than a current income perspective. So this graph here is looking at breaking people up by income at that time. Now, when you break up people by measures of permanent income, you tend to find less of a difference between the four groups. So there's a much higher correlation between income and consumption shares of these products in the cross-section than there is with permanent income. And so if what you really care about is, it's not about this year versus next year, but like overall lower income versus higher income guys, the pattern doesn't look quite as bad. And that's a point that Paterba has made. another point when thinking about incidence is from a behavioral point of view, you might actually think that it's a good thing that we're raising prices in affected quantities a lot for low-income individuals. Because if people have self-control problems, the incidence is likely to be beneficial because they're actually smoking less, right? So remember that we look at prices as a measure of incidence, not because we just care about prices per se, but because we think when people are optimizing, making them pay more for something is bad for them. Now, so it reduces their utility. What we ultimately care about is like the distribution of utilities and profits in the economy, right? Now, if these people are actually not maximizing utility, so they're consuming more cigarettes than they should, then by raising the price, I'm increasing their utility because I'm bringing them closer to their optimum. And so it's actually a good thing that I'm raising, that the incidence is being passed through rather than being absorbed by the companies. Maybe I want the incidence to fall on the consumers from this perspective, right? So it's not totally clear.
Social efficiency, right? We just
Yes.
focus on the equity.
It's purely on how are we splitting up the pie. There's no issue of optimal, sort of the level of production or efficiency. It's separate. Okay, the third point that I want to make, this paper by Ada and Corniglia in the AER in 2006, it's something at least I would not have thought of, is that there's an intensive versus extensive margin in smoking cigarettes. So what they show is that when there are higher taxes, people smoke fewer cigarettes, like number of cigarettes, but they smoke each one for longer. So that's like, you haven't targeted the tax at the right thing, right? You're taxing the number of cigarettes, not how much you're smoking them. And so they use data on cotinine, which I guess is a biomarker in your lungs that measures the level of inhalation. And they show that that is not responsive to the level of tax rates, even though the quantity consumed is responsive to the level of tax rates. All right, so maybe you aren't actually, so coming back to this Gruber thing, this tax is not accomplishing the goal of actually getting people less of this cotinine biomarker in their lungs, which is perhaps what you care about at the end of the day. Okay, so that's what I have on cigarette taxes. I'm now going to move on to the other examples. Okay, so the next one we're going to do quickly because it's a similar diff and diff method, but it's like really well done, which is why I want to cover this. So this paper by Hastings and Washington in 2010, the question they have is, how do food stamps affect grocery store pricing? Okay, incidence of food stamps on pricing at grocery stores. Now, the key fact that you need to know for this is that food stamps typically arrive at the same time for a large group of people. So everybody, for example, gets their food stamps on the 1st of the month or the 8th of the month or something like that. Varies across places. Now, because of that, you basically get a big demand shock at the beginning of the month, where you see this anecdotally, like if you look at grocery stores, they know that they need to stock up at the beginning of the month, especially in high poverty areas, because lots of people are going to come in to buy stuff when they get their food stamps. So the first thing they test is whether demand changes at the beginning of the month. Notice that that is a way to test the permanent income hypothesis, because the exact time at which I get my income should not affect consumption. Now, it can affect it if I'm consuming durables, right? Like if I'm stocking up on cans of soup at the beginning of the month, that's fine. But what they're actually going to show you is that even for non-durables like perishables, like fruit, people buy a lot more stuff. And like even caloric intake is much higher at the beginning of the month than later in the month, which is something that's been documented quite clearly in the literature. Now, so that's the quantity question. But that gives rise then to the incidence question, because stores know that they're getting this big outward shift in the demand curve at the beginning of the month. So what's the natural profit maximizing response for the store? It's to increase prices, right? Lots of people want to come and buy stuff. You might as well charge more in the first week. And so that's what they want to investigate. Are these big grocery chains basically benefiting from food stamps instead of the consumers? So they use scanner data from several grocery stores in Nevada. And they use data from stores in high poverty areas defined as having more than 15% food stamp recipients and low poverty areas in order to get these two different treatment intensities. And then they have data from club cards, those cards you use when you check out to get discounts, on whether each individual uses food stamps to pay for their purchases. So they have, at the individual level, variation on whether you used food stamps or not, and then at the store level, variation in the number of guys who are showing up with food stamps. Remember, it's the store level variation that's relevant for incidence, right? Because the store cannot price discriminate. They can't say, if you pay with food stamps, we're going to charge you $2 for the bananas, and if you don't, we charge you $1, right? So the incidence is going to occur at the store level rather than the individual level. And then they use data from other states where food stamps are staggered across months as a control. And so the point you can see here, what's very nice about this, what makes it really convincing, is there are lots of dimensions of counterfactuals. They're going to use variation across stores, across individuals, and time of the month to measure these pricing responses. Okay, so here's the first result on changes in expenditures across stores. You can see this non-parametric regression with dummies. And let's talk about the red box first. Okay, so the way to interpret these coefficients in the red box are by what percentage does expenditure fall in weeks 2, 3, and 4 relative to week 1, which is the baseline excluded week where there's a zero, by construction the coefficient is 0, okay, right? That's the baseline level of demand. And so what this is showing you is that in week 2, demand is 20% lower than in week 1. In week 3, demand is 29% lower than in week 1. In week 4, it's 33% lower. So this huge drop-off in purchases at the store relative to the first week. So that fact was actually known from prior work, that there's a huge drop in demand for food stamps recipients. So benefit household is an indicator for using food stamps. Now what the blue box shows you is just the weak dummies for non-benefit households, right? So this is the same trend for people who are not using food stamps, and you see this thing is almost perfectly flat. So there's a 2% drop and then like a little bit of a drop in the later weeks, but it's trivial. It's an order of magnitude smaller than the drop for food stamps recipients. So you know, it makes sense that there's a little bit of a drop for people who don't have food stamps. You might stock up at the beginning of the month when you get your paycheck or whatever, but this is really what's of interest. Okay, so that's the quantity result. And then the question is, what do the stores do in response to prices? So they're going to look at the high poverty stores and the low poverty stores separately. And so what you can see here is that in the high poverty stores, prices are a couple percentage points, 2 to 3 percentage points lower in weeks 2, 3, and 4 relative to week 1 of the month, the beginning of the month. But in the low poverty stores, where you don't have many food stamps guys showing up, it's totally flat. So the stores are, in fact, increasing prices by about 3% when demand goes up by about 30%. Okay? So some of the incidence of the food stamps program is being captured by these grocery stores because of the way in which they're paid out. But really, you know, I think the way we should look at this is that problem is not that bad. The stores are not raising prices that much, given the tremendous surge in demand at the beginning of the month. And you know, this is another nice check that they do. So they say, how do prices change for each of these products from the first week to later weeks? That's what the x-axis is. And then the y-axis is how does quantity change for each of these products from the first week to later weeks. And so, you know, take an example like number 30, prepared frozen foods. They do it by category. So they're basically repeating the previous two tables for each category and then scattering the quantity and the price estimates, right? And so as you'd expect, like something like prepared for frozen foods where you can stock up, you buy a lot at the beginning of the month. Big reduction in quantity from week 1 to later weeks, and also a big price increase of almost 10% for prepared frozen foods at the beginning of the month, because you know lots of guys are going to come in and stock up on this stuff. So you can see how, you know, they have a number of dimensions of counterfactuals that make it quite clear that this mechanism is actually operating. Now, from a theoretical point of view, what I find interesting about this study is actually not what the focus of the paper is on, but I think there's interesting work to be done in this area. It's that why is the subsidy not having that much of an effect on the price? All the food stamps recipients are basically being insulated by the fact that there are lots of non-food stamp people in the same market, and you can't price discriminate across these guys. So even in the high food stamps areas, it's like 15 or 20% of the people are showing up with food stamps, right? And so you've got this 80% customer base, which if you raise prices a lot in the first week, you're going to drive all those guys away, right, to a different store. And so the equilibrium is such that because you're pooled with others, you end up having better distributional effects. And so that's very interesting because it suggests that if you have a subsidy that's targeted too narrowly to one group, and they all shop together, or they're all in a separate marketplace, you could end up having the incidence taken by the supply side, which is typically not what you want. And so, take an example of that. Take the earned income tax credit. The labor market tends to be quite segmented by skill level, right? So I might pay guys who are doing an $8 an hour job a different amount when they all show up with the earned income tax credit subsidy, because $8 an hour guys are in a different market relative to $30 an hour guys who are not getting the EITC subsidy, right? Whereas in the grocery store, you don't have that type of segmentation. And so it might actually be better from an incidence point of view to give subsidies in contexts where you have this sort of pooling. And so one of our students, Peter Ganong, is actually writing as part of his thesis a paper on housing vouchers and showing that similar effects are playing in that market as well, where the degree of concentration of the subsidy really affects incidence. Okay, so we talked about the EITC subsidy. So that's the third and final paper we're going to talk about on incidence applications. Asks exactly this question. How does the earned income tax credit affect wages? Now you're going to see with this paper that it's asking a much broader, more diffuse question. And so the identification is going to be much, much messier than the Hastings and Washington. But it's still an impressive effort to understand this important program. So EITC payments, as we've discussed, subsidize work and transfer money to low-income working individuals. The concern is that that subsidy could be taken by employers who are shifting the wage. So for example, if you have inelastic demand for low-skilled labor and elastic supply, we know that wage rates are going to adjust one for one with the EITC. That is, the employer is going to completely capture the incidence of the program. So that's the key policy question. Are we actually transferring money to Walmart, or are we giving money to low-income individuals through the EITC? Okay, so what Rothstein is going to do in this paper is consider a model of the labor market that has three types of agents. Of course, there are employers, but then there are two types of workers. There are EITC eligible workers and there are EITC ineligible workers. So for example, think about people with kids versus without kids. If you're earning $10 an hour and you have 2 kids, and I'm earning $10 an hour and I don't have kids, we're basically in the same labor market, but you get the subsidy and I don't. And he's going to show you that there are different distributional effects across these two groups, which is why in the model it's important to split them apart. So what he does in the paper is extends the standard partial equilibrium incidence model to allow for differentiated labor supply and different tax rates across demographic groups, which is what's going to produce these different types of workers, eligible and ineligible. That heterogeneity is going to be a double-edged sword, as you'll see. It's going to permit identification. So the fact that some guys are eligible and others are not is going to help you identify the impacts of the policy. But it also makes it incredibly messy because some of the incidence of the policy is going to fall on the ineligible guys, and that makes the whole thing much more complicated. So at a broad level, the research design here is to compare wage changes across groups who were affected differently by expansions of the EITC program from 1992 to 1994, where the program was expanded quite a bit, and then it was later further expanded as well. Okay, so sorry, I should have actually said from 1992 to 1996, essentially, is when the treatment is occurring. So here's what the EITC schedule looks like in 1992 for people with 1 and 2 kids. As a function of your earnings, what's the size of the subsidy? So it's this familiar pyramid shape, which I showed you in the first lecture. And you can see that it's like relatively small, right? So it goes up only to about $1,200. Then in 1996, it became much bigger, especially for people with 2 kids who could start to get subsidies of up to $3,500 roughly. Okay, so people with 2 kids who were in a low income range got a big treatment going from 1992 to 1996, and people with no kids essentially got no treatment because there was no EITC for people with 0 kids prior to 1996. And people with 1 kid got a moderate sized treatment. So the number of kids coupled with your income level is the key dimension of treatment here. All right, so to summarize that, the first thing Jesse does is plots average tax rates for various demographic groups. And what you can see here is that for people who do not have kids, for people who are not married and have 2+ kids, there's a big drop in the average tax rate if they're low wage earners. So x-axis in all of these figures is your hourly wage rate. Okay, so the way to think about this is, think about it completely on the extensive margin in the context of this paper. So I am deciding whether to work or not. If I work, I earn $10 an hour, $15 an hour, $20 an hour. That's what's on the x-axis. So if I come in here at $25 an hour and start to work, like a full-time job, I'm already past the EITC. So I'm not getting anything out of this. But if I come in and I'm a $5 an hour guy, I get this like 20% reduction in my average tax rate. So big boost to, for my incentive to work if I have 2 kids, but much smaller if I have 1 kid and no change if I have no kids, okay? So that's just the treatment, all right? So now he's going to draw a bunch of graphs that look like this for outcomes, wages, quantities, and so forth. So what's the problem in doing this? There are 2 main challenges in identification. The first is that the EITC expansion occurred when the nation was coming out of a recession, the 91 recession. And so you can't do the pure time series, obviously, for that reason, for many other reasons. And so you compare to other workers like EITC ineligible or people with slightly higher incomes. But then that leads you to the second problem, which is that there are violations of the common trends assumption, which he himself establishes using pre-period data. So there's skill-biased technical change where there's differential demand for low and high skilled workers. The recession also may have differential impacts on people with slightly lower and higher incomes. We know that lower income people tend to suffer more in recessions and then rebound more quickly when we're coming out of recessions. And so all of that makes it impossible to just do a simple diff and diff, as I will show you. And so what he ends up doing is comparing the trends after the reform relative to the trends before the reform, which, as we talked about, is the triple diff type of analysis. And exactly as we talked about before, it's hard to really convince yourself that you've nailed it once you're in this situation, but he does the best he can, given the constraints. So there are 2 dependent variables of interest, as usual, prices and quantities. Prices are measuring how wages change for a worker of a given skill level. Okay, that's going to be important. We'll see that. Second, the quantities measure how demand and supply for workers of each skill level changes because of the EITC. And so the overall logic here is that we use these 2 moments, the wage and the quantity change, to back out the slope of the supply and demand curves. And that actually relates to the answer to the question you asked early on, but I'll come back to that later. So once you have these 2 moments, you can back out the slopes of both the supply and demand curves. And then he's going to be able to do his incidence analysis. Okay, so let's now talk about a problem that arises in this type of study and a technique that's useful to fix it and fix other problems as well. So what's the ideal test to measure the incidence of the EITC? It's to look at how the wage of a given individual changes when the EITC is introduced relative to a similar but ineligible individual, right? Now the problem in the data is that he's going to use repeated cross sections. So he's going to use the current population survey, which surveys a different set of guys in the US periodically. And so as a result, you don't see how the wage rate changes for a single person, right? Now, a related problem, even if you didn't have this data issue, is that even if you're tracking one guy's wages, you might not want to do that because often we see that there are wage rigidities, right? So if I'm making $10 an hour at Walmart, the way Walmart adjusts to the EITC is not by taking the guys who are making $10 and saying, now I'm going to pay you $9 because you got the EITC, because wages tend to be downward nominally rigid. It's rather that when you hire the new batch of guys, there's a lot of turnover, you hire new guys, you hire them at $9 instead of $10, okay? So it's not even clear, even if you did not have the repeated cross-section problem, that you'd want to track the same guy over time. Okay, so for both data limitation and economic substance reasons, you're going to need to look at wages of different people. And what's the fundamental problem here? It's that we know when you expand the EITC, more people start to work, right? And so now you have a different composition of people in the labor market. And so if you just compare mean wages after and before, you're not holding the skill level fixed. You're not looking at the same person. You're looking at a product of different mix of guys now working and wage rates changing. And you need to disentangle those two. So the technique that he's going to use, which is a very useful technique and relates to the synthetic matching, is a reweighting procedure that allows you to, in some sense, track the same skilled worker over time. And this is the DiNardo, Fortin, Lemieux paper. Okay, so what's DFL reweighting? So it seems like it can be a little bit hard to understand when you look at the paper, but it's actually very simple. So what DFL reweighting does is essentially generalizes propensity score reweighting in order to examine changes in distribution semi-parametrically, conditioning on observables. So let's do this completely in the context of an example. So let's suppose that wage rates are purely a function of your height. So in fact, there's a paper by Andy Postlethwaite and others, and as well as earlier work, showing that taller people do in fact earn higher wages. So every inch, I think, is worth a 2% wage increase, just empirically. All right, so let's say for simplicity that height is the only thing that determines your wages. And let's say when the EITC is expanded, the average observed height of workers falls because less skilled, that is shorter people, enter the labor force, right? So what's the logic here? There's some fixed cost of working. Before the EITC was in place, I didn't want to pay that fixed cost. I wanted to stay home and take care of my kids instead of work. But now the EITC is there, and so it's worth it for me to find somebody to take care of my kids and go work. And so the lower skilled people are going to make that choice, and that's going to drive down the average height of the people who are working in this example. Okay, so what we want to do is identify how the wage distribution changes for people of a fixed height. So for guys who are 5'6", what happens to wages before versus after the EITC is expanded, right? So how are we going to do that given that we can't track a given guy? We're going to hold fixed height semi-parametrically by reweighting the distribution of wages ex post to match the heights ex ante. So let's do this numerically so it's clear what I mean. So let's say you've got 100 short people and 100 tall people pre-reform, and 200 short people and 100 tall people post-reform, because these 100 extra short guys entered the labor force after the EITC was expanded. So you want to have the same mix of short and tall people before and after in order to accurately calculate the impact of the reform on wages holding fixed skills, right? So what you want to do is put 2/3 weight on the tall and 1/3 weight on the short when calculating the wage distribution after the reform. Because you basically have, the problem is you have too many short guys relative to tall guys after the reform, right? So in particular, you have twice as many short guys relative to tall guys. So in order to undo that, you put twice as much weight on the tall guys relative to the short guys after the reform, so that you have an equal mix of tall and short guys after the reform, just as you did before the reform. So more generally, the point is you reweight the distribution of characteristics after the policy change to look exactly the same as it did before the policy change in order to deal with this composition effect, okay? And what's nice about their technique is that when you compute these propensity score weights and then basically just plot a histogram with those weights, weighting the counts, right, by these propensity scores, you can just see visually how the distribution changes accounting for the skill changes. So what's the key assumption here for causal interpretation of the changes? It's that all the selection is occurring on observables. So in this example, it works well because I've assumed that the only thing that matters is height, and I measure height without error, and I can reweight on height. But more generally, if selection is occurring on some unobservable thing that affects your weight, that affects your wage, then then you're going to have a problem. But so this is why the reweighting approach doesn't get you out of the need to have a quasi-experiment, but it's a good way in conjunction with an experiment to to form the right control group so that you're isolating the difference of interest, like we saw in that Arizona example that I was talking about earlier. So let's see what he actually does in the data. Okay, so this is the first graph, does not involve any DFL reweighting. It's totally straightforward. This is just the change in total labor supply. Think of this as percentage change in total hours of work, all right? What's the main thing you see in this graph? This one up here is really sharply upward sloping. That is, people who were earning really low wage rates are much more likely to work after the EITC reform. They work a lot more after the EITC reform relative to before. So this is a basic labor supply response. When I give people a bigger incentive to work, more people work. That is a very well-known fact, one of the most solidly established facts in the literature on labor supply, that when the EITC was introduced, lots of low-income single women with kids entered the labor force. You just see that in the raw time series in the US aggregate data. Okay, and then he's showing you that in the other control groups, you don't see nearly as much, which makes sense. Now, what I want to do then is look at the changes. So let's actually skip. So this is intensive margin changes. I'm going to skip this in the interest of time. So he's distinguishing intensive and extensive margin. Let's not worry about that for this purpose. The main point here is that most of the changes on the extensive margin, the probability of working at all rather than the number of hours you work conditional on working. But let's get here to the wage changes, which is what I'm interested in the context of incidence. So here he's doing the DFL reweighting, right? He's saying, I'm going to make everybody look the same in terms of demographic characteristics, age, et cetera. So, for example, lots of single women with kids entered the labor force. So we've got a lot more single women with kids after relative to before. So let's put less weight on the single women with kids so that we get the same distribution of characteristics, right, before and after. Okay, so what do you see here? So first of all, what do you expect to see from an incidence point of view? What should you see in that upper right box? So labor supply curve is shifted outward for low-skilled workers. What should we see happens to wage rates? Yeah, it drops in particular. What for whom on that graph? Yeah, the lower wage guys, right? So this thing should look like it's upward sloping, right? Because these guys should have gotten the biggest wage cuts. The wage growth rates should have been the most negative for these guys relative to these guys. So you don't see that. In fact, you, if at all, see something that looks like the opposite at the very bottom. All right, so that is the first thing that he shows, that the basic diff and diff of like this relative to that does not work. You get the perverse wrong sign implication that wage rates actually went up when you introduced the EITC. Okay, so then what he does is says, potential explanation, demand curves shifted differentially, higher demand for low-skilled workers in the 1990s, and that led to a particular wage change led to wage increases for those guys, which contaminates this thing. So it would have looked like this, but because of that differential demand shift, it tilts it like this. Okay, so that's conceivable. So to deal with that, he repeats the same analysis for 1989 to 1992, a pre-period. Okay, so imagine drawing exactly the same graph, and now difference this graph relative to that graph. Right, so that's where you get the triple diff, all right? And now what he shows you is that that changes the sign back to what's expected. So we won't go through this whole table. What I want to focus on here are these numbers. What are the impacts on wage rates, changes in wages, as a function of changes in the average tax rate? And you see that when the average tax rate is cut in the left two columns, which are the straight DD, the negative coefficients here imply that when average tax rates are cut, wages go up, which doesn't make sense. But here you get the positive coefficient, which is what we'd expect from theory. But you're left to wonder, like, is this right? Is this right? Did we correct for the trends correctly? It's not totally clear, okay? But he's going to report as his preferred estimates these triple diff estimates over here. And so let me just wrap up on this paper. So he concludes that wage elasticity estimates 0.7 for labor supply, minus 0.3 for labor demand. What are the ultimate implications for incidence? If you take those estimates at face value, EITC eligible workers gain about 70 cents per dollar of EITC expansion. Employers gain about 70 cents per dollar. So Walmart is basically taking 70 cents per dollar of the EITC if you take the estimates directly. And EITC ineligible low-skilled workers are getting hurt because it's like, if I don't have kids, my wage is getting cut, but I'm not getting the subsidy. So I end up paying a price of 40 cents, and then that gets shared between these other guys. On net, we only achieve 30 cents of redistribution towards low-income individuals for every dollar of the EITC. So you can see that we spend $50 billion, we maybe get much less money in the hands of low-income individuals. This is potentially a serious critique of this policy, but my sense is we need to do much more empirical work. It's suggestive we need to do much more empirical work to figure out what's actually going on. And so just last thing, like why is that? What are the caveats? So we talked about the recession creating differential trends. You have no clean counterfactual. You don't have a solid research design. You don't have panel data, which really is a complicating factor. You can't figure out short run versus, you're trying to identify short run effects. The effects could be very different in the long run because of wage rigidities. And lastly, it's a pure extensive margin analysis. So like we talked about, the way he's thinking about it, it's all about whether you work or not and how that's a function of the average tax rate. But the intensive margin impacts would actually go the other way, because for lots of people who are on the phase-out region of the EITC, your wage rate is actually falling when the EITC is expanded because your marginal incentive to work more hours is being reduced. And so then the thing is totally reversed, and this analysis doesn't really take account of that. So a bunch of caveats, but I think an interesting exercise.